My name is Kerstin Forsberg. I work as an associate professor here at the Department of Chemical Engineering at KTH, Royal Institute of Technology, and I work at the main campus here. And I'm very glad that I've been given the opportunity to be here today and to give this presentation on how to create resource recovery. So, I work in a research group where we develop novel processes and techniques for resource recovery from wastewater and from primary and secondary raw materials. And secondary raw materials can be end-of-life products, for example, or various waste materials. And I work together with my colleague, Zeynep, and we manage different research projects, we supervise students, and we teach on various topics connected then to resource recovery. And we work, of course, not just together with the people in our group, we also work with other people at KTH, and nationally and also internationally. We work with people in academia, and also in companies, of course. And maybe you are a bit curious about this picture I put here. It is a picture of a crystal of iron 3-fluoride 3-hydrate. And it's from a project many years ago in another research group. And I put it there. Why did I put it there? Because it's nicely connected to resource recovery. So when you manufacture different parts in stainless steel, the steel goes through a heat treatment, and there is an oxide scale layer forming on the surface of the steel. And before you sell your steel products, you want to remove this scale layer. And what you do is that you put your steel in contact with acid mixtures. And what happens then is that the steel actually dissolves in the acid, and in this way you can remove this scale layer and get a new shiny surface on the steel. But what happens here is that over time the mixed acid will contain more and more of these metal ions, and you can only use this acid mixture up to a certain point. When the metal ion concentration is too high, you have to start over with new fresh acid because it loses its ability to pickle. And then you end up with this waste mixed acid with a lot of metal ions in it. And what was done at that point was that it was neutralized, and then it was put on a deposit. But we worked to develop a process how to recover the acid and also the metal value. And this was a project in collaboration with IVL, the Swedish Environmental Research Institute, located just here next by. And we developed a process combining nanofiltration and crystallization to separate out the metal ions as metal fluoride hydrate crystals, so that the acid could be reused, and also we could get some value from the metal content. So it's a nice example of a project on resource recovery. This is a car. A car contains a lot of different materials, and when these different materials and components reaches the end of their lives, of course it would be good if they could be recycled, or if the value in them could be recovered in some way. But in order to motivate such a process to recover the value, of course there need to be some value in these components. And the European Union has put together a list of critical raw materials. This is raw materials that are critical to Europe because they are used in the manufacture of various products in Europe. And these products are also used and sold. But in combination, there is also a risk for security of supply of these raw materials. And thus they are put on this list of critical raw materials. And one group of elements that are on this list of critical raw materials are the rare earth elements. And I will come back later in my presentation to what the rare earth elements actually are. But you can find rare earth elements in many different parts of a car. You can find them as additives to the glass, You can find rare earth elements in LED screens. You can find rare earth elements in electric motors in the car in the form of magnets. And you can, if you have a hybrid electrical vehicle with a nickel metal hydride car battery, you can find a lot of rare earth elements within this battery. And actually we have one project in our group where we want to recover the valuable elements in a car battery. So I will come back to that also later in my presentation. The rare earth elements are also used in many other high-tech products in use in today's society. So scandium is one of the rare earth elements, and it's used together with aluminium to form alloys that are light and strong, used for the aircraft industry. And also scandium is used to produce solid oxide fuel cells. You have a lot of rare earth elements within nickel metal hydride batteries, as I said before. And rare earth elements are also used to produce very strong magnets. And these magnets can be used then in electric motors, or they can be used also in wind turbines. And then rare earth elements are also used for luminescence purposes. So, waste is what is left when imagination fails. This is a nice quote I got from a professor at Chalmers, Christian Ekberg. And I like it because there is a huge potential in what you can recover resources from different waste materials still. And actually less than 1% of the rare earth elements were being recycled in 2011, and it's not much better today. And this could be due to many different reasons. Inefficient collection is one thing, but technological issues is another. Maybe the processes on how to recover these rare earth elements actually doesn't exist at the moment. And there could also be a lack of incentives. So legislation is very important here as well. One approach could of course be to design your products already from the beginning so that they could be easily recycled and that you could easily recover the valuable elements. This is also an interesting approach. We are trying to develop different processes to recover valuable elements from various waste materials. One thing that is interesting here with resource recovery from waste materials is that many times the product development goes to developing products with less and less content of these valuable elements because it makes it more cheap to produce your products if it's possible. But for the perspective of recycling the products, this is actually a bad thing because then you get not as much value in your waste products as would otherwise be the case. So it's even more challenging to construct an economically sustainable process on how to recover these valuable elements and to recycle the materials. So I'm a chemical engineering person, so of course I wanted to show you where in the periodic table of the elements you can find the rare earth elements. So the rare earth elements is a group of different elements, so it consists of the lanthanum and the whole lanthanide series going from cerium to lutetium. And also scandium and yttrium are grouped as rare earth elements. And all these elements are grouped together because they have very similar properties. They all form trivalent ions in aqueous solutions. And the ionic radius of these elements is very similar. So they have very, very similar properties, and thus it's very challenging to separate them from each other. Also, it is very challenging to know how to separate out the rare earth elements even as a group and other elements as well from a given waste material. You can compare it perhaps a little bit with chess. So in chess there are a limited number of opening moves, but then as the game develops, possibilities multiply enormously. And this is the same thing if you have a waste material and if you want to recover the valuable components of this material. So many times you start with the same few operations. Maybe you dissolve your material in acid. But then there are so many different separation techniques that can be applied and separated into a whole process in different sequences. So it's not at all obvious how to develop a process to recover the value in what you want to recycle. So at the moment, I'm involved in 3 different projects where we are recovering different valuable elements from different waste materials. So in this project, furthest to the left, we are working on recovery of scandium, which is one of the rare earth elements. So there's a lot of value in scandium. And this is actually a part of a larger European collaboration project funded by Horizon 2020. And in this project, we want to recover scandium from bauxite residues, which is a residue when you produce aluminium, and also from an acid waste from titanium dioxide pigment production. And the work here at KTH is focusing on recovery of scandium by crystallization into a solid phase that is very pure and that is also suitable for further processing. Then in this project in the middle here, this is a project in another research group I'm collaborating. Here we're working with an apatite concentrate. This apatite concentrate is a byproduct when LKAB processes its iron ores. And it contains a lot of phosphorus and also many of the rare earth elements. And I will come back to this project later in my presentation as well to describe what we're doing here. And then the third project here, we are recovering the valuable elements from nickel metal hydride car batteries. And the valuable elements here is nickel and cobalt. Cobalt is also on the EU list of critical raw materials. And also a lot of the rare earth elements are in there. And what we do here is, this is also a collaboration with IVL, the Swedish Environmental Research Institute. What we do here is that we actually dissolve the active anode and cathode materials in acids, and then we investigate different ways and different ways to combine different separation techniques to separate out the valuable elements from these waste materials. Going back first then to this Midproject here, we want to recover phosphorus. Phosphorus is also very valuable. And phosphorus you use to produce fertilizers. Production of fertilizers constitutes about 88% of the global phosphorus consumption, actually. And fertilizers deliver increased crop yield, which is important for a growing population and also for the production of biofuels. And production of fertilizers engages many, many companies within the European Union. And the main phosphorus deposits are located outside of Europe, and 90% of the phosphorus used in Europe is actually imported. And thus, phosphate rock is listed as one of these critical raw materials. So, do we have any phosphorus sources in Sweden? This is the question. So, you know now we have also the apatite concentrate from LKAB. It contains a lot of phosphorus because it's an apatite. And also there is some value in rare earth elements in there. So we want to process that. And then we also have this ashes, which is a source of phosphorus that we have even in Sweden from incineration of sewage sludge. Looking at phosphate valorization, so you have phosphate ores, could be apatite. Also, you process that to produce phosphoric acid, and then the phosphoric acid, much of it is further processed into fertilizers, or you can produce the fertilizers directly from the phosphate ore. But there are also secondary raw materials. Sewage sludge and leachates contain some phosphorus. But even better, if you want to recover the phosphorus, is first to do an incineration and recover the phosphorus from the ashes. And there is work on how to do this. Then we have phosphogypsum, which is waste material when you produce fertilizers from phosphate ore through the sulfuric acid route. And it still contains some phosphorus and also some rare earth elements that are of value. So it could potentially be processed to recover this, especially if you can also get out some other valuable end products within this process. So maybe you can potentially create an economically sustainable process to process the phosphogypsum. So we are working with the apatite concentrate we got from LKAB, and we want to recover both the phosphorus and the rare earth elements. So we are looking at this approach here. This is an existing process to produce NPK fertilizers. And you can use the apatite here as an input. And you contact the apatite with nitric acid. And then you do a cooling crystallization, so you get out the calcium nitrate tetrahydrate, which is also a valuable end product. And then you do a neutralization with ammonia. And you add potassium salts, and you have evaporation and particulation, and you get your NPK fertilizer in the end. So we have been looking at, in this process, how to also recover the rare earth elements that you find in the apatite within this process. And you can do this by applying a solvent extraction operation directly after the digestion to recover the rare earth elements as a group. Or you can look at the partial neutralization to extract the rare earth elements right after the cooling crystallization. And this is the approach that we have been working with in our group. And here you get out the rare earth elements as a rare earth concentrate together still with a lot of impurities, and all the rare earth elements are together in a solid phase as phosphates. And so in order to, in the end, get more value out from the rare earth elements, maybe we want to separate them into their individual elements. Then they are worth more than a mixture that is also very impure. So this is what we have been developing. And here you have to combine different separation techniques, actually. Both precipitation and solvent extraction techniques is what we have been looking at. And so the separation techniques that we have been looking at in our lab is specifically crystallization and a specific type of solvent extraction operation called supported liquid membrane extraction. And crystallization is, of course, when you have your compound or dissolved in a solution. And then you want to create a supersaturation, so you want to exceed the saturation point so that you get out your compounds in a solid phase as crystallization. So it's the opposite of dissolving something. And you can create your supersaturation by different ways. You can, for example, remove the solvent by evaporation, or you can work with temperature, but there are many other techniques as well, depending on what you want to separate. In supported liquid membrane extraction, it's a specific type of solvent extraction operation. Here you have your feed phase, which contains a lot of different elements. And in our case, we want to separate out the rare earth elements from this mixture. And so you put this feed phase in contact with a membrane. And in the pores of this membrane, you put an organic phase. And the organic phase contains a diluent and extractant molecules. And the extractant molecules are can then bind selectively to the elements you want to separate. So in our case, we use an extractant that binds specifically to rare earth elements. And then on the other side of the membrane, you have your strip phase. So this is another aqueous phase where you want your rare earth elements to be transported to. So what happens here, you have a specific conditions in the feed phase so that the rare earth elements form complexes with the extractants in the membrane. And then these metal organic complexes diffuses over the membrane to the strip side where the conditions are different, so that the rare earth elements are released from the extractant molecules, and then you find them in the feed phase instead. So this is the principle of the separation, and we have put together one of these setups in our lab with a flat sheet membrane so that we can study the transport of the metals over the membrane. But in industry, you would like to have more surface area in contact with each other. So you could use then instead these kind of hollow fiber membranes. So this unit here contains a whole bundle of very thin hollow fibers. And each hollow fiber looks like this. And in the walls of these hollow fibers, the walls are porous. So in the walls, you put the organic phase. And then you have one of the aqueous phases going outside of the fibers and the other organic phase going inside the fibers. And then you have the separation over the membrane in this way. So we also have one of these flow sets in the lab also to study the separation. So we are working in order to recover different valuable elements from different waste materials, applying these techniques in our research group. And so it's great fun. So thank you so much for your attention.